Hi, I'm Mark Stephenson, and today I'll be sharing my paper comparing probabilistic roadmaps in reinforcement learning for the relative motion inspection of space objects. The motivation for the inspection task comes from the increasing prevalence of rendezvous, proximity operations, and docking type missions. It's important to understand the RSO, or the resonant space object, that you're interacting with before you operate on it. These operations may be to prepare for docking. You may want to identify damage on an asset before repairing it. You may need to characterize a target before preparing to capture it for deorbiting. Or perhaps there's an unfamiliar space asset that you're trying to characterize. In all of these cases, there's an inherent risk present in proximity operations. We need to avoid any possible collisions. So the specific problem statement we're looking at is we want to inspect all illuminated portions of an RSO while minimizing both the thrust and the time we're using. There are a few constraints on this problem. This includes that our control is based on impulsive burns followed by passive drifts, so we're really trying to leverage the natural motion in the low Earth orbit. Our inspection is limited by the instance angle of our illumination source, the sun, whether we're in eclipse, and our range and instance angle relative to the RSO. Finally, we assume that our RSO is nadir pointing and in some arbitrary eccentric low Earth orbit. Here's a short video showing the inspection task in progress. We can see in the upper left what our inspecting satellite is viewing on our RSO, and in the center we can see inspected portions in green, illuminated portions in yellow, and uninspected and unilluminated portions in gray. In this work, we're going to be looking at two methods for the inspection task. These are reinforcement learning and probabilistic roadmaps. For reinforcement learning, we're going to get a closed loop planner. This is going to give us responsiveness to unexpected tasks or unexpected changes in our environment, and is going to be really good if we're in a low communication availability environment. On the other hand, probabilistic roadmaps are going to give us an open loop planner. That means that we need to have good understanding of when and where our activity is going to take place, and we need to have sufficient ground contact availability to actually upload these plans. Reinforcement learning has very low onboard compute requirements, which is why we can use it in a closed loop manner, whereas the probabilistic roadmap-based approach will require offline computation to generate trajectories. We are going to see that reinforcement learning does have a slight optimality gap relative to those probabilistic roadmaps, but that's really the trade-off that we're willing to make. Are we wanting to spend a long time generating optimal solutions on the ground, or are we okay with close to optimal solutions in a closed loop environment? And depending on your mission type, either may be acceptable. Finally, there's ways of introducing safety guarantees to both these methods. With reinforcement learning, we can implement shields, which we presented previously. And for probabilistic roadmaps, we're generating inherently safe trajectories. The main question of this work is, how do these two methods stack up in an apples to apples comparison? To do that, we're going to test both methods in the same environment using the package BSKRL, which is a reinforcement learning environment for satellite tasking problems that the AVS lab has been developing. This takes Basilisk, which is our fast and flexible open source simulation framework, and combines it with the standard Gymnasium API for reinforcement learning environments. As a result, we get these configurable environments for satellite reinforcement learning research. Previously, we've done such work with it, including Earth observation tasks and the RSO inspection work presented here, among other scenario types. This package is fully open source and available online, so please check out our documentation and the source code. We're going to start by talking about reinforcement learning, the first method we're considering. To do this, we need to formulate our problem as a Markov decision process. We start by defining our observation space, which includes both information about where our inspector is relative to the RSO, also information about the orbit, where the sun is, and how much delta V we've used so far. Finally, we also need information about what parts of the RSO have or have not been inspected yet. Our action space matches the control scheme in the problem formulation. We're going to have a 4-element continuous control space, with the first three elements being the impulsive thrust we're going to perform, and the fourth element being the passive drift duration that we're going to travel along after taking that controlled action. The rewards in the environment are as follows. We're going to have an inspection reward for incrementally increasing the amount of the RSO that's been inspected. We're going to give a completion bonus when we've inspected all of the points that are illuminated given the orbit that we're in. We're going to have a fuel use penalty that's parameterized by alpha. So this parameter is important because it's going to induce different behaviors on our time versus fuel Pareto friend. And finally, we're also going to yield a failure penalty if we enter an unacceptable or unsafe state. To train these policies, we're using reinforcement learning, which very briefly has an agent try randomized actions in an environment in order to, over time, find the policy that maximizes the long-term reward. We train multiple policies using RLlib's implementation of PPO using a relatively small policy network. Training these networks takes about 40 million steps, which is about 2 days of compute time or 750 years of simulated time. As we vary the fuel use penalty for each policy, we're going to see these different behaviors. Low fuel use penalties are going to create more aggressive policies that use lots of fuel and complete the task more quickly. The more we increase that alpha parameter, penalizing fuel use, we're going to get slower but more fuel efficient trajectories. Now let's move on to our second method, probabilistic roadmaps. Probabilistic roadmaps are a planning technique from the robotics and motion planning communities. In short, this algorithm samples roadmap points. So for our problem, those are going to be points in both space and time, represented by mean anomaly. And this is going to allow us to sample the points in a smart way where we're only sampling points that are over regions that are inspectable at a given time. We can connect the edges between these points by solving the two-point boundary value problem, since we have analytical solutions for relative motion under first-order eccentricity. And once we have built that graph, we can find a solution that minimizes fuel and time used with a mixed integer formulation. To improve upon the solution, we can repeat a process of resampling points around our solution trajectory, resolving the mixed integer problem, and repeating until we've achieved a solution that we're happy with. The mixed integer problem for this graph is somewhat complicated. In our objective, we have a zeta weighted fuel cost term and a 1 minus zeta weighted time cost term. This is very similar to the alpha parameter in the reinforcement learning formulation, allowing us to guide our solver to solutions that either favor fuel efficiency or time efficiency. We have constraints that yield traveling salesman problem-like single path generation, preventing loops or disconnected solution components. We also have a constraint that limits our maximum delta V that can be performed at any maneuver. And finally, we have a success condition which matches the same inspection threshold of illuminated points that we see in the reinforcement learning based solution. Now that we have our two methods defined, we can compare them. We'll start by looking at example trajectories in two cases. In the first, we have a high illumination case, so this is a case where most of the RSO is illuminated at some point over the orbit. We can see that our reinforcement learning and PRM-based methods produce qualitatively similar solutions, though they are quite different trajectories ultimately. We see a similar thing in a low illumination case, where only 1/2 of the RSO is illuminated over the course of the orbit, so this is like a sun-synchronous orbit type of situation. And again, we have qualitatively similar trajectories from the two methods, but by no means identical. These two trajectories were picked with somewhat arbitrary values of alpha and zeta, so the tuning parameters for our respective methods. But the big question we want to answer is, how does the fuel and time efficiency compare across all possible values of zeta and alpha, depending on the method we're using? To look into this, we're going to plot some fuel time Pareto fronts. So on the left, we're going to solve the problem for a varying value of zeta for a set of initial conditions. And on the right, we're going to do the same for a varying value of alpha. The right side points each correspond to one of the policies we saw on that training curve slide. We can then repeat this process for many different sets of initial conditions. We have 20 in the probabilistic roadmap case due to its computational time, whereas in the reinforcement learning case, we're going to try for 1,000 cases each. We can then average the performance at each of those values of zeta or alpha and get a Pareto front for the mean performance of each method. And for the ease of visualization, we're going to move that red line for the PRM Pareto front over to the right graph and vice versa. And we can see that, unsurprisingly, the probabilistic roadmap is performing better than reinforcement learning, but not significantly so. This really is going to come down to a trade-off for your mission type. If you need to have that closed loop responsiveness of reinforcement learning, it will come at the cost of half an orbit or half a meter of second more fuel used. But if you have sufficient information about your environment before you're having to complete the task, probabilistic roadmaps will save you some time and fuel, given that you have the opportunity to plan and upload your plan. Just to further highlight the computational difference of these two methods, we can see the cost of PRMs on the left and of RL on the right. The PRMs are taking about 10 minutes to solve for each case, whereas reinforcement learning is a negligible amount of time that could be easily computed on board. So, in conclusion, we've demonstrated two low fuel solutions to the inspection problem that leverage relative motion dynamics. This formulation really is novel compared to the rest of the literature because by leveraging these natural motion dynamics, we're looking at more like 2 meters per second of fuel used as opposed to 20 or more seen in other work. And as I talked about previously, the choice of method is really going to depend on the mission requirements. If you have a high certainty environment where an open loop plan is going to work, the probabilistic roadmaps are going to save you some time and fuel, but reinforcement learning is going to give you responsiveness to potentially changing or unknown or uncertain environment at the cost of slightly more fuel or time. Thank you for listening to the presentation, and please check out the paper on our website.